Okay, now moving on towards to back actually to the stiffness matrix derivation from the strain energy formulation, we found out that the unknown that we had in that formulation was the strain. The strain was dependent on the displacements. The displacements were, although partially derived with respect to x and y, actually depended upon natural coordinates r and s in our formulation, or in our assumption that we started with. So we made this transformation with the Jacobian, and now I want to use that Jacobian to find out this particular change in the derivatives. So if I want to write dou u dou x and dou u dou y in terms of dou u dou r and dou u dou s, I can just basically put the transformation that I just derived in the previous slide as it is. So I have minus j21 and j11, and in the same way I will have dou v dou x and dou v dou y, also 1 by determinant j, j22 minus j12 minus j21 and j11. So I'm just basically using the relation that I derived in the previous slide to apply it to dou u dou x, dou u dou y, dou v dou x, dou v dou y, to be transformed to dou u dou r, dou u dou s, dou v dou r, and dou v dou s. So now we have all the partial derivatives with respect to each other using the transformation Jacobian. Now, since we want to combine these equations in a certain format so as to get the unknown strain epsilon in the by using dou u dou x, dou v dou y, dou u dou y plus dou v dou x, we can just pick those particular values from within these matrices here. I can name these as equation B and C. So I'm going to use equations B and C to get epsilon to be equal to 1 by determinant of j with this entire matrix. We will decide how big it has to be in terms of dou u dou r, dou u dou s, dou v dou r, and dou v dou s. Now this is a vector which is 4 by 1. The epsilon is a vector which is 3 by 1. So in order to be able to get to the right dimensions, we need this particular matrix to be equal to 3 by 4. That is what we need. And of course it's quite simple because we only need 3 strains, so we can fill in 3 rows corresponding to dou u dou x, dou v dou y, and dou u dou y plus dou v dou x. And if I pick out the right terms from the equations B and C, I will end up with something that looks like this: minus j21, j11, minus j21, j11, j22, and minus j12. This is something for you to check, so I would really urge you to work with me alongside. So you're also working out the same problems. Pause the video, check if you get to the same point. If not, go through it again to see where you made a mistake. So once we have this relation for the strain and the displacement, we also know that the displacement vector right here has u and v, which depends on r and s because of the shape functions. So we can also now expand the this particular vector. So we can write dou u dou r, dou u dou s, dou v dou r, and dou v dou s. Of course, we know that here u is equal to n times u and v is equal to n times u, where u is of course all the different degrees of freedom, and n is a function of r and s. Then I can easily do a partial derivative of each of them with respect to r and s and get a certain large matrix which would relate these values particularly to the degrees of freedom: uix, uiy, ujx, ujy, umx, umy, unx, uny. So we need to get a certain matrix where, of course, this is 4 by 1, this is 8 by 1. So we need to get a matrix which is 4 by 8 so that we can get the right dimensionality. So if we pick up these particular functions here, u and v, that we described before in the natural coordinates, and do a partial derivative of each one of them as we require to be put into this particular matrix here, we will end up with a 4 by 8 matrix, which looks like this. You have minus 1 by s, 0, 1 minus s, 0, 1 plus s, 0, minus 1 plus s, and 0. Sorry, I don't have too much space here. I sort of messed it up in the beginning. And then this line will be 1 by 1 minus r, 0, 1 minus s. Sorry, this is also r, 0, 1 plus r, 0, minus 1 plus r, 0, and so on. And you will be able to fill in all the terms over here. In the short notation, to make it very simple for you when you are setting up the program to work this out, if the Jacobian matrix with the prefix inverse determinant, that is right here, this one is given as matrix A, and you have this matrix, which is the prefix, which is the matrix relating the displacement with partial derivative of the displacement with respect to natural coordinates with the local degrees of freedom. If this matrix is matrix M, then we can define, if we go back to this particular definition right here, I want to stay at this slide. If I want to write this as A times M times the degrees of freedom U, I can also write this as B times U. So B is actually equal to a product of matrix A and matrix M. So my final relation, therefore, is epsilon is equal to BU, where you will be easily able to find out what is B by finding out what is the Jacobian and then what is the relation between the partial derivatives of displacement with respect to natural coordinates and the relation with respect to the degrees of freedom. Now, if there is still a certain doubt about how I arrive at this particular relation, you can start with the displacement. So I can write this u as niui plus njuj plus nmum plus nnun. And I can write instead of ni as 1 by 4, 1 minus r, 1 minus s, ui, and so on. And then I will do a partial derivative of dou u dou r, and here I will be left with 1 by 4, and this will be gone. And that way I'll be able to define a certain derivative here, and that's where I get ui out here and the term into this particular matrix. I hope that is clear to you. Now, once we have derived this particular relation as epsilon is equal to Bu, we will get back to our strain energy definition, which we stopped at with equation A right here. So let's go back to the end of these slides. So now strain energy was given as dA epsilon transpose d epsilon, this was times dE, and here there was a half and a dA. Now we can replace the epsilon transpose with B and U times transpose. We can do that quite easily. And then finally we can also write dA to be equal to the area is given as dx dy, and if I want to transform dx dy to dr ds, dr ds, then I need to multiply it with the determinant j for doing the transformation, as you might have understood by now, and substituting all of that in and also doing a partial derivative with respect to all the different degrees of freedom of this strain energy term, I'm going to get the stiffness matrix, the K of the element, which can be written as the thickness of the element times double integral for the natural coordinates dr ds minus 1 to plus 1 minus 1 to plus 1, B transpose, D, B, determinant J, dr, ds. So of course one of these is for the r and one of these is for the s. And all the terms are now known to us. We can easily find these out, substitute it back in, and get the stiffness matrix Ke. If you work this out, then because there are 8 unknowns in the system, you will get a stiffness matrix which is going to be a 8 by 8 square stiffness matrix with 4 components of U and 4 components of V that you started with. I hope this is clear. If you have questions, please don't hesitate to put it on the discussion board for further clarification.